Welcome, everyone. Today, we'll be exploring normalizing flows, a powerful family of generative models used for density estimation and data generation. This tutorial will cover the fundamental concepts, mathematical foundations, differences from GENs and VAES, and key applications in AI and machine learning. Let's get started. Normalizing flows are a class of generative models that use a sequence of invertible transformations to map a simple distribution, like a Gaussian, into a more complex distribution. The process is guided by a bijective function, ensuring that we can transform the data forward and backwards seamlessly. This property is crucial for density estimation and efficient sampling. A normalizing flow consists of two key components: base distribution, a simple distribution, typically Gaussian, which serves as the starting point; transformation, a sequence of invertible transformations applied to reshape the base distribution into a complex data distribution. Before diving into normalizing flows, we first introduce the change of variables formula, a fundamental concept in normalizing flows. This formula enables us to compute the probability density function of transformed variables. Let C and X be random variables which are related by a mapping G, such that X equals G of Z and Z equals G inverse of X. The probability of X is given by the formula displayed, where X and Z need to be continuous and have the same dimension. The formula involves computation of the determinant of a Jacobian matrix, which is very challenging. Now, let's look at the normalizing flow model shown on top. Let Z denote a latent vector, and X an observed example. Z follows a Gaussian distribution P0. The function G is an invertible transformation that maps Z to X. The log determinants of the Jacobians of the transformation can be explicitly obtained. Alpha represents the trainable parameters of G that under the change of variables, the distribution of can be expressed as the equation displayed at the bottom. In the normalizing flow, the mapping G is typically composed of a sequence of transformations. By stacking multiple transformations, we obtain a progressively more complex representation of the data. The final transform distribution is what we use for density estimation and data generation. Let H with subscript I represent the intermediate output of the IEH transformation. Then, we can rewrite the probability distribution of X by decomposing the determinant of the Jacobians of G into the product of the determinants of the Jacobians of all individual transformations that make up G. The normalizing flow model chooses transformations whose Jacobian is a triangle matrix, so that the determinant can be efficiently computed as the product of its diagonal elements. Since the normalizing flow model provides an exact likelihood, we can train it using maximum likelihood estimation. This is a key advantage of flow-based models compared to most other generative models. Suppose an observed training dataset X is given. Maximizing the data likelihood can be achieved by a gradient ascent algorithm, which requires computing the gradient with respect to the model parameters. The carefully designed architecture of transformations in flow-based models ensures that gradient computation remains efficient and tractable. Now, let's look at the architectural structures of normalizing flows. To effectively use normalizing flows, there are several key architectural requirements. First, dimensional consistency. The input and output must have the same dimensions. Since we are applying invertible transformations, we cannot change the dimensionality. Secondly, invertibility. Every transformation must have a well-defined inverse, which allows us to compute likelihoods efficiently. Thirdly, Jacobian determinant computation. Since the change of variables formula involves the determinant of the Jacobian matrix, we need transformations where this determinant is computationally tractable. Many flow-based models are designed with these constraints in mind, leading to innovative architectures that balance expressivity and efficiency. The structure of normalizing flows plays a crucial role in their effectiveness. In practice, we often use a large number of transformation layers to ensure the model is expressive enough to capture complex data distributions. Many key advancements have been made to improve the efficiency and flexibility of normalizing flows. Notable contributions include the introduction of planar, radial, Sylvester, and householder layers, which have greatly improved the expressiveness and scalability of normalizing flow models. Hopefully, you have gained a basic idea of what the normalizing flow are. Now, let's compare normalizing flows with two other popular generative models, generative adversarial networks, GAN, and variational autoencoders, VAE. GANs generate highly realistic samples but lack explicit likelihood estimation, making it challenging to assess the probability of generated data. Additionally, they suffer from training instability due to the adversarial process. Unlike VAEs and normalizing flows, GNs do not have an inference mechanism, meaning they are designed solely for generation rather than dimensionality reduction. VAEs, on the other hand, provide explicit likelihood estimation, but this likelihood is lower bounded, meaning they do not achieve exact density estimation. A common drawback of VAEs is that they tend to generate blurry images due to the assumptions in their latent variable modeling. However, their approximate inference mechanism enables efficient embedding extraction and dimensionality reduction. Normalizing flows, in contrast, allow exact likelihood estimation, making them mathematically rigorous. They are also more stable to train than GANs, though they can be computationally expensive due to the requirement of invertible transformations. Each model has its strengths and weaknesses, but normalizing flows offer a unique balance between expressiveness, stability, and likelihood estimation. Normalizing flows have been widely applied across various domains. Some key applications include 1. Image generation. Flow-based models can synthesize realistic images by learning complex data distributions. 2. Video generation. They can also be extended to generate video sequences, modeling both spatial and temporal dependencies. 3. Point cloud generation. Useful for 3D modeling, normalizing flows help generate structured 3D point clouds. 3. Anomaly detection. Since normalizing flows model explicit probability densities, they can detect rare and unusual events by identifying samples with low likelihood. 4. Bayesian inference. Normalizing flows improve variational inference by enabling richer, more flexible posterior distributions. Let's take a closer look at each of these applications. The first application is image generation, where flow-based models have achieved significant progress. A notable example is the 2018 paper, GLOW, Generative Flow with Invertible 1x1 Convolutions, which improves upon earlier architectures by introducing invertible 1x1 convolutions. This innovation enhances the model's ability to capture spatial correlations in images, making normalizing flows a strong contender for high-quality image synthesis. Normalizing flows can also be applied to video generation, where both spatial and temporal dependencies must be modeled. A notable example is the 2019 paper, Video Flow, a flow-based generative model for video, which extends normalizing flows to video synthesis by capturing dependencies across multiple frames. This demonstrates how normalizing flows can go beyond static images and be effectively applied to dynamic generative tasks. The figure displays 3 different features for 2 sets of conditioning frames, showcasing diversity in outcomes. Another exciting application of normalizing flows is in 3D point cloud generation, which is important for computer vision and 3D modeling. The point flow model extends normalizing flows to represent and generate 3D objects as point clouds. The figure displays examples of point clouds generated by the point flow model. From top to bottom, they are categories of airplane, chair, and car. Since normalizing flows allow for exact likelihood estimation, they are highly effective for anomaly detection, which is the process of identifying rare or unusual events in data. For example, MS Flow models complex distributions at multiple scales, allowing for better identification of outliers. By computing likelihoods explicitly, normalizing flows can determine whether a given data point deviates significantly from normal patterns. This figure demonstrates some results obtained by the MS Flow model. It straightforwardly displays the localization results of each single-scale and multi-scale on 4 industrial products, whose defective region sizes vary wildly. Normalizing flows have also been applied to Bayesian inference, where we aim to estimate posterior distributions in probabilistic models. In the original variational autoencoder (VAE) framework, approximate inference is parameterized by a standard encoder with a reparameterization trick, typically assuming a Gaussian distribution. However, Using normalizing flow to parameterize the inference model enhances its expressiveness, making it capable of capturing more complex posterior distributions. This motivates the use of flow-based model for variational inference. To be specific, the latent variable z is first drawn from a simple based posterior distribution, such as a diagonal Gaussian, and then transformed through a normalizing flow. Since flow-based models allow for exact likelihood computation, the log likelihood of the inference model P of z given input x is tractable. Ultimately, by integrating the flow-based model into the VAE loss function, we obtain a new, tractable VAE loss with a flow-based variational inference component, as shown at the bottom of the slide. To summarize, normalizing flows provide a powerful and mathematically rigorous approach to generative modeling. These models transform simple distributions into more complex ones through invertible mappings. In contrast to GNs and VAES, normalizing flows enable exact likelihood estimation and offer stable training. Flow-based models have found widespread applications across various domains, including image, video, and 3D point cloud generation. They are also effective for anomaly detection, as they learn the distribution of normal data and can identify outliers. Additionally, flow-based models can serve as a parameterization tool for the inference model within the variational autoencoder framework. Thank you for your attention. I look forward to discussing the next topic with you.